Hello everyone, welcome back. Today we're going to be learning multiple forms of searches and sorts. So let's get started. So the first two are linear and binary search. I covered it in the previous video, but just in case if you don't know it, I will go over it one more time because it is quite a common concept and you should build up upon that. So first up is linear search. So linear search basically goes through each and every element. So we have, I have a set of numbers, and we have 1, 2, 5, 6, and 7. And my goal is, hey, I want to reach number 7. That was a bad circle. But in order to reach number 7, I would have to jump through so many numbers. And that's why this isn't considered to be the best or most effective method. But it is quite popular. This is not popular, like it's well known, but in programming, you won't use it a lot once you become a more developed and have more experience in coding. But here is an example of linear search in coding form. So here I have an array, and then here is my for loop. And basically this for loop is just iterating through the array, through each and every element the way we want it. And this if statement is saying, hey, if basically I says I is increasing, the index is changing. So if x suppose is 7, so if 5 is 7, no. 6 is 7, no. 7 is 7, yes, then return 7. Otherwise, if my supposed number was 8 and I didn't find 8 here, then it would have returned -1 because 8 is not in this list. Just keep in mind that linear search has to be sorted, meaning that it has to be organized numerically from least value to most. Time complexity quite high, big O notation. And I think you can logically tell why it takes so much time. Reason being because we have to go through each and every element. But we have a much more effective method, and this is called binary search. And basically, I have a list of numbers, 1, right? Same set of numbers I'll actually take, 5, 6, 7. Keep in mind that these numbers aren't always going to be the same, but I'm just doing this, as an example. So we split it in half. And we keep on doing so if we reach your desired number. So let's pick the same number again, 7. So what I'll do is first to see the middle of the number in this set. So that would be 4. Is 7 greater than 4? Yeah. So I'll just erase the 7. So we can already eliminate 1 to 3 because we know that our number has to be greater than 4. Okay, now we have these numbers left. Now I take the middle of this. Okay, 6. Is my number greater than 6? Yes. Eliminate these numbers. Is your number 7? Yes, it is. So see how that only really took me like 3 attempts to find my number, whereas in linear search, it would take me much more longer time. So that's why binary search is more effective, much more popular. And we can also see that in terms of time complexity, it is also less, it's in the log, which requires much less time. Keep in mind, this has to be sorted as well, right? Our 1 was our least number, so it was in the first, and the 7 was our highest, so it's in the last. And then int L, we can see here in this loop how this would be iterated. And then here, basically, this splits it in half. Okay, this splits it in half. Basically, this would be my code for reaching the number 4. then this statement is saying, oh, if 4 equals 4, like if the part where you are at right now is actually the value we're looking for, then return that value. So suppose instead of looking for 7, I was looking for 4, then I could be like, oh, return 4. But if that's not the case, we have these two cases. This one is saying if, suppose let's take 4 is less than our desired number, then ignore the left numbers and keep on incrementing to this, your higher numbers. Whereas our else statement is saying, okay, if else, just look at the decreased numbers, right? Eventually, if these two cases don't turn out, then we return -1. Reason being, again, if my number was 8, 8 was not located here, so it would return -1. Reason why out of all the numbers we return -1, it's just programming languages. We do, it's just a number, this negative, so we just do that. But yeah. Okay. One thing I do want to mention about binary and linear is that in this right now set of numbers, our worst case was 7, right? Which I did pick to really emphasize how bad linear search is. But our best case scenario could have been 1 as well. So yes, this is like, could be our best case, but most of the time, this is not our best case, right? And most of the time, it's not even that drastic. So our average case could have been, 4, around 4, but still it's much less efficient than what we're doing here, right? So just keep that in mind. Okay. Next up, we're here to jump search. A little bit more unique, a little bit more newer concept, which you're learning. So here I've mentioned its time complexity. So its time complexity is actually between linear and binary, meaning that its time complexity is much less than linear. So that's good news. But it's much, not much, but like it's higher than binary search. So why would we favor this over binary search? Well, there are some instances in jump search. So first, let's explore jump search, and then I'll go back on why we sometimes say jump search or binary search. Okay, so jump search here, it basically skips a certain amount of times. So maybe if I had the same set of numbers, 1, 2, right? I should have written these numbers before. I apologize about that. 7, we have these 7 numbers. And in binary search, okay, we go in between. Jump search, no, we would skip maybe a number of steps. Maybe, you know what, I'll add an 8. So maybe we would like to go 2. So instead of going linear, actually I'll do, I'll do 2, it's fine. Right, then we'd go, okay, 1 is not my number. Is 3 my number? Is 5 my number? Is 7 my number? But what if the number is even? Then what it does, jump search, it goes back again and finds your number. So in this case, there was a good number, 50% of chance that our number was odd, and we would have been able to find our number much more quickly. Just in case, if it wasn't able to do so, then we would have repeated backwards. Reason why we pick this method over binary search is that jump search only goes back one time, whereas binary search may go back multiple times. So that's the reason why we favor jump search, if that makes sense. So yeah, so this case it was 2. Maybe if I had higher set of numbers, like such as I had 9, 10, 11, 12, and maybe instead of 2, I picked 4, then we can see how it's, much higher, right? Like 4, 8, 12, and then we might have to go back again, but still there is a possibility of finding these numbers. So that's just how jump search works, and that's the reason why it's time complexity, higher than linear, but lower than linear, and higher than binary, but some instances this is favored over binary. So this is a good method to know. In terms of code form, so basically here we have step, and this is basically determining how much we're moving, right? That's our 2 or our 4, which we decided later on. So this piece of code is deciding how far do you want to move. Then we would move, and right, this is the code for moving with your steps. But then we have a piece of code right here, and it's basically saying, oh, we didn't find it. If that doesn't happen, then do that linear search. Then start from the beginning and go through that linear search if you don't find it. Then, sorry, I have a little snippet of code right here, and it says, okay, even when you're done with the linear search, right, we only do the linear search once. And even if you don't find it here, then just return -1, that this element was not found over here, even though we tried to. But if you do find your element, then return it. Hey, in our linear search, we did find it, so we are now returning it. And yeah, so that's pretty much it for jump search. So our next one is interpolation search. Pretty sure I pronounced that wrong, but I tried my best. So in this one, again, has to be sorted, right? Numerical order, decreasing to increasing numbers. But the second one is it has to be uniform. And what do I mean by uniform? In the sense that the gaps or intervals between to this should be around the same. So obviously we can't have exact, right? It's very special that all the numbers you get in a coding scenario, just flow perfectly and would be +3, +3, +3, +3, +3. But try to have the most uniform as you can have it. So here we have 3, 3, then it goes 1, 2, 1, 2, then 4, 2, 1, 1, 4, 4. But still, this is uniform because we have to realize that we're whenever we're coding, we're not gonna have the perfect case scenarios. But this is still not that bad. So this search takes less time than binary search. But the thing with binary search is that binary search doesn't require your numbers to be uniform. All it requires is that your numbers are sorted. This method requires your numbers to be uniform as much as you can. So that's why sometimes using this search is not the best idea, and sometimes it's just better to stick with your binary search, even though this takes this time. But suppose I wanted to find the number 29, right? I'm always with the highest numbers. Okay, but I want to find the number 29. How do I find that? So this search actually has like a whole formula. Like binary search has one too, but it's just like going in the middle. But this one actually requires you to know the formula. If you can't read my messy handwriting here, then I did take a little screenshot of the formula and posted it here. Sorry for it's really small, but so my number I want is 29. It's just by chance I picked the highest number, but typically, it's whatever number. So it could have been 13 if I want to pick 13, etc. Minus your lowest number. So my lowest number is 1. So I'm -1. So 29 minus 1 is 28. Then you would pick your highest index. Remember, this is index, like your 12th number, not what is your number, but like which number, if that makes sense. So your index. So it's 12, and then my lowest index number is 0. So 12 minus 0 is 12. And then here's your highest number, which is, by chance I'm picking my highest number, but that's 29. And my lowest number, which is 1. So this is 28. So now you would do your math. So when I do 28 times 12 divided by 28, I get exact 12. And remember, this gives your index. And is my number 12? Yes, it is. My index is 12. So we were able to find 29. Remember that this is our best case scenario. First try, first attempt, we got it. But it is not always going to be like this. Let's take maybe 20, right? And maybe not take a number which is, the highest. So basically, 20 there. Everything stays the same, except that my x is 20 and not 29. So I will do the math. So 20 minus 1 is 19. 12 divided by 28. So 19 times 12 divided by 28 gives me 8.14. Problem is none of our none of our indexes are 8.14. It's either 8 or 9. But we'll round it to 8. Okay. Patricia, my number was 20. And this is showing that my number was 19. No worries. We will just take it, right? One thing to keep in mind is that 19 is lower than 20. So now, instead of 1 being our lowest number, 19 will be. So basically, this part of the array, I don't care. We literally don't care about it. Now I'm just going to be sticking with this part of the array. Right, so 5 numbers, and here we go. Our aim is to get 20. So it's 19. So now we have some changing to do, meaning that 1 isn't our lowest number. It is now 19, which is our lowest number. Right? So that's one change. It's now not 12 minus 0. It is 12 minus 8 for our index. So I'll just change that. This becomes 1. This becomes 4. And then now it's not 29 minus 1. It is 29 minus 19. So this would become 10. Now this is where I was mentioning about where our low comes in. Oh my god. Okay, I erased that for a second, sorry. Our lowest comes in. So our lowest was 0, right? Our 0 index. But now our lowest is 8. So we can add 8. First we'll do this math and then add later on. So 1 times 4 divided by 10 is 0.4 plus 8. We get not 8.14, but 8.4. And index, again, it would lead up to 8, but 8.4 is quite close to 9. And remember, these numbers aren't perfect. and neither is the index. But we did, if you notice, get closer to 9 than we were earlier, right? From 8 that's not a dot, 0.14 to 8.4. I mean, that's a plus. Maybe, you know, if the numbers were more uniform, we would have gotten a higher decimal, but that just didn't work out for us in this case, right? And maybe, you know what, I can even double check the math. 20 minus our lowest index, 19, not index, element, 19. Then 12 is our highest index, 8 is our lowest index, sorry, it was 8. And then 29, highest number, and then 19 was lowest. We were just unable to, and that's okay. And you know, maybe in this case scenario, this number we got it first try, best number, exact. But this one, not so much, and that's completely fine. Might show you why. Maybe if our numbers were even more diverse, it would have been much harder to use this search. So that's why there are cons and pros with binary and then interpolation search over here, but it just depends on which number of values you have. So that's pretty much it for today. If y'all enjoyed this, then I'll make a part 2 of this video. And yeah, to see y'all next time. Bye.